open-air Van de Graaff generator, which we're lucky to have because it was built by its namesake, Professor Robert Jameson Van de Graaff, who invented and built this very machine. He completed this machine in 1933. It was not the first thing he's built, but it's one of the largest. And he used it and the powerful electrical forces that it creates to push tiny atoms to extraordinary speeds and then smash them up against targets. So that when they broke apart, scientists would have a better understanding of what atoms were made out of and the forces holding them together. Now, since then, better atom smashers have come along. So in 1955, it was donated by MIT to the Museum of Science. And since 1980, we've been using it for shows on electricity. But we no longer use those powerful electrical forces to smash atoms. Instead, we use it to make really big, really bright, really loud sparks. Now, because those sparks are even louder where I'm at, and because I do the show several times a week, I'm going to be wearing hearing protection. So when you see me put my hearing protection on, I highly recommend that you cover your ears tightly as well. I also want to make note that to ensure that everyone can exit out of the theater, we can't have anyone standing or sitting in front of that doorway in the lower right. So if you're on the red carpeting, make sure that you stand up and then sit on the blue carpeting. In the very unlikely event of a fire, we have direct exits out of the museum underneath the exit sign in the rear right-hand corner of the theater on the lower level. If you're on the mid or upper levels, there are the exit signs back and to the right. Now, it's one thing to warn you about bright flashes and loud noises, and another to give you a taste of what you're in for. So once again, it's my great pleasure to introduce one of the world's largest open-air Van de Graaff generators. Now, give me time to cover those ears. Now, if you'd like to see more sparks, first of all, if you like those sparks, let me hear you say, yeah! If you'd like to see more sparks, let me hear you say, yeah! If you'd like to see me get inside that cage when it's struck with those big sparks, let me hear you say, yeah! Well, that's exactly what I'm going to do. And to illustrate an aspect of lightning safety, why you're safe inside a car or a building from a lightning flash during a thunderstorm. We'll talk about that at the end of the show. But before we do, it's worthwhile knowing more about what we're going to talk about. Now, the first thing I want to say is that electricity is a very confusing word. It's confusing because that one word can mean a lot of different things. We're going to find out that electricity can mean electric charge, the force that moves that charge, the energy that the charges have, or the number of charges that are moving. So instead of using that one word, which can mean a lot of different things and generate confusion, we use the specific terms wherever possible. We're going to find out that electric charge and the electric force that moves it are completely invisible, that they interact with each other and with magnetism. And you might say, well, electricity is invisible, then what were those big sparks that we just saw and heard? We'll answer that question, as well as demonstrate some aspects of lightning safety as I get struck inside the metal cage behind me, and at the very end, an indoor symphony of sparks, where I turn on all the devices behind me. So, that being said, let's go back and carry on. And for that, I'd like to ask if there's a volunteer out there, a volunteer that's got some longer, straight, dry hair.
Straight, dry hair.
All right, come on up. Let's give a volunteer a big round of applause. Della, this will work best if you take your hair tie out. And I want to thank you for being such a brave volunteer, because you just volunteered to have your hair electrified to well over 1,000 volts. Now, to do so, Della, I'm going to show you some cutting-edge technology. You'll be astounded at how high-tech this device is. You ready for this? 1, 2, 3, ta-da! It's a balloon. Now, raise your hand if you think that this is the oldest trick in the book. In fact, you may not realize how old this trick really is. The trick that we're about to do, Della, was first done in 600 BC by a Greek named Thales of Miletus. Now, of course, they didn't have balloons back then. So instead, our word electricity comes from the Greek word electron for amber or fossilized tree resin. Because when Thales rubbed it up against Earth, he discovered a force between the two. Della, you and I are about to find out that electric charge is not just in batteries, it's in everything. And to prove that to you, I'm going to use the electric charge in this balloon and your hair. You might remember that everything is made of these teeny tiny things called atoms. Although they're too small to see, careful experiments have shown that there's positive charge on the inside of every atom and negative charge on the outside. Both kinds make the electric force, but each makes it the opposite way. And since normally there's equal amounts of both types sitting one on top of the other, the pushes and the pulls cancel and we don't notice it. But Della, if we separate that charge, if we put the negative charge in one place and leave the positive charge behind, we'll notice the force between them. That can be done as easily as putting two different materials in contact with one another. So I'm going to have you hold this mirror so you can see the results of our experiment. And I want you to stand right in front where everyone can see it. And zoom in just a little bit. And Della, may I rub this balloon against your hair? Would that be okay? All right. When I put the balloon up against Della's hair, I'm going to be taking negative charge off of her hair and putting it on the balloon. That's going to charge the balloon negatively, and it's going to leave her hair positively charged. And once we separate that electric charge, that's going to give rise to a hair-raising electric force. Yeah! Della's hair didn't change color, nor did the balloon, and that proves to us that electric charge is invisible. Nor can we see the force that's moving Della's hair around. Because although we can see that her hair follows the balloon wherever it goes, proving that there is an attraction between opposite types of charge, we can't see the force that's moving her hair. What we can see is that the strength of the electric force gets weaker the further the charges are apart, and it gets stronger the closer the charges are together. Now, Della, these are effects between opposite types of charge. Would you like to see what happens when we get charged of all the same kind? I'm glad you're such a good sport, because now you volunteer to have your whole body electrified to tens of thousands of volts. Another big round of applause, please. Now, to electrify your entire body, we're going to use the small Van de Graaff generator that works the same way as the large machine behind me. Now, even though it's called a generator, the charge is initially separated by the power plant using magnets and coils of wire. We'll talk more about that in a moment. When the charge comes to us, however, Della, the energy that the charges have, or their voltage, is too low. To jack that voltage up from about 100 volts to well over 10,000 volts, in this machine we leave positive charge behind in the ground. Negative charge goes on a rubber belt here inside this plastic column. We use a motor to spin the belt around, and it's the work that the motor does in pulling the charge on the belt further away from opposite charge in the ground. That work is what increases the energy of the charges, and thus their voltage, before they're collected here on this metal sphere. Della, you might remember that metal is a good conductor, meaning that charge can travel easily through it. But plastic and air are good insulators, meaning that charge has a hard time moving through them. What I'm trying to say is once we put the charge up here, it's stuck. It can't go through the air or the plastic, so it just builds up. But it's not just going to build up on the metal dome, it's also going to build up on you. To keep that charge moving back together with opposite charge will be left in the ground, I'll have you stand on this insulating wooden platform. I'm going to have you put your right hand on the metal. Keep your left hand down by your side. We'll zoom in once again. When I turn the machine on, I'd like to have you briefly shake your head back and forth like you're saying no. That'll loosen up the hair on your head, and we'll see what effect all that charge has on your hair and body. Are you ready? Gently shake your head side to side. Shake your head like you're saying no, Della. Keep going. Shake, 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 shake. Now forward and back like you're a rock star. All right, stop shaking, Della. Turn around and move area. Come on. We're over here. Nice. All that negative charge on Della's hair is pushing away from the charge on her body. Proof that charge of the same kind repels or pushes away. Now, Della, I just turned the machine off. Are you still electrified? Don't worry, that'll go away in a couple years or so. I'm just kidding. Della, watch what happens to your hair as you reach out and touch my hand. Della, what did you feel? Did you feel a zap? I know I sure did. What happened to your hair when you touched me? It went down. It went down because when you touched me, the charge that was on you went through me to get back together with the opposite charge in the ground. With those charges neutralized, most of them, there's a lot lower electric force. You still got a few hairs stand up. So if you step down off the platform, any remaining charge recombines with the opposite charge in the ground, and the forces are balanced and you're back to normal. Let's give Dell a big round of applause. Thank you very much. A lot of fun seeing Della's hair stand on end here inside. But if your hair stands up like that outside, that's a warning that lightning can strike at any moment. It means you're underneath an electrified thunderstorm. And it means that you need to get inside a building or a car as soon as possible. And in a moment we'll talk about why those are safe places to be. But before we do, you may notice a lot in common between electricity and magnetism. In particular, you might remember that there are two poles in every magnet, north and south, and we've just found out that there are two types of charge, positive and negative. We found out that opposites attract and likes repel, and that's true whether we're talking about electric charges or whether we're talking about magnetic poles. We're about to find out that electricity and magnetism are even more closely related. But to show that to you all, I'm wondering if there's two big, strong volunteers out there. Two big, strong volunteers. All right, come on up and come on up. Let's give our volunteers a big round of applause. Ronan and, what's your name? Zevin. Now, Ronan and Zevin, you both look very strong indeed, and in fact, you both look considerably bigger than this tiny AA battery that I have here on the end of a bit of wire. Now, Ronan and Zevin, would you imagine that you're stronger than this tiny AA battery? That's what we're going to find out. Ronan, I'm going to give you a flat plate of iron, and I want you to hold that like you would the handlebars on a bicycle or a motorcycle. Zevin, you get a plug of iron with a coiled wire wrapped around it. Now, man, you hold that in a similar fashion. Okay. Ronan, take a couple steps back. Zevin, take a few steps forward. All right, so Ronan, I want you to have you stand right over there. Zevin, step right up here. Gentlemen, I want you to turn and face each other and walk forward so that you meet in the middle, put the flat half so that they're touching. And pull them apart. Are they magnetized? No. Was that easy or hard? Easy. It was easy and they're not magnetized. But watch what happens when I use this tiny AA battery to move electric charge through Zevin's coil of wire. Let's put the flat halves together once again. Then I connect my tiny AA battery. Zevin and Ronan, this is important. Put one foot way behind the other. Keep your weight centered between both legs. Don't lean back or put your feet together, because if you do pull them apart, I don't want you to hit the ground or hit the guardrails. On the count of 3, I want you to pull. 1, 2, 3, bow! 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 Moving charge can make a powerful magnetic force. Are they magnetized? Is that easy or hard? Hard. But if I disconnect the tiny AA battery, and you give a slight tug, and you put the flat halves together once again, and pull them apart, are they magnetized any longer? No. Is that easy or hard? Let's give Ronan and Zevin a big round of applause. Ronan and Zevin did an outstanding job showing us that moving charge makes magnetic forces. Now we're going to see if magnetic forces can move electric charge with this. It's a flashlight, but instead of batteries inside, the only thing it has is a magnet. That magnet can move back and forth inside a coil of wire, and that coil of wire is connected to a light in the front. We'll be able to see if the magnet moves charge in the coil of wire by looking at the light. Now, with neither the magnet nor the coil of wire moving, the light is dim. And that tells us that magnetism has no effect on electric charge if neither is moving or changing. But if I do some work and I move the magnet through the coil, yeah! Here we go.